Hi there, welcome to the NUPOC video study guide number 100. We're going to continue with our geometry by calculus problems now, and we'll build on the last problem, which was finding the area of a circle by calculus, and now we're going to find the volume of a sphere by calculus. So we're going to use a similar approach to the last problem here. I'll try to draw a sphere as best I can. And we are going to use, instead of just polar coordinates, we are actually going to use spherical coordinates to make this integral a lot easier. It would be a nightmare if we tried to do this in rectangular coordinates. So our coordinate system is going to have an r hat direction like this, pointing out from the center of the sphere. It's going to have, going around this equatorial plane like this, that is going to be our, not d theta, that's going to be our theta hat direction. And then going up over the poles like this is going to be our phi hat direction. So let's go ahead and put together our integral here. So like we did in the last problem, we're going to start by integrating, I'm just going to draw this as a solid line in the background here so we can I kind of screwed it up a little bit by drawing this dotted line that went all over the place, but anyways, so this is the back equator here, the equator going around the back of the sphere. So again, we're going to integrate dr out from the center to the edge of this circle that's in the equatorial plane. Okay, so that is going to be, let's see, that is going to be, of course, 0 to r, right? Again, if we're saying that the distance from the center to the perimeter is r, so that'll be 0 to r, dr, like we had last time, and then we're going to move, we're going to start sweeping around d theta, right? We're going to start sweeping out this circle in the equatorial plane to get its area. So this little section right here, in the previous problem, that was just r d theta, but now in this problem, that is actually going to be a little bit different. It's going to be r sine phi d theta, and the reason for that is, after we sweep out this area, as we start to sweep these individual areas, right, from the equator down to the pole, right, and then up to the pole up here, this width between these two lines going out from the center is going to change, right? Because think about it, at the equator it's full width, but if we say that one of the poles is down here, right, this line is going to come down here, and this line is also going to come down, and they're going to join at the pole here. So the width between them, right, the width of this section is not the same down here close to the pole as it is up here close to the equator. And so the factor sine phi takes care of that. If we say down here this is phi equals 0, and at the pole up here we say this is phi equals pi, right, then we have sine phi is 0 down here and 0 at the pole, and maximum at the equator, where phi equals pi over 2 at the equator, right? Okay, so now let's go ahead and put this term into our integral. So we're going to be integrating over d theta, and the factor is going to be, this shouldn't be big R, this should be little r, sine theta sine phi d theta. So this will be r sine phi d theta, okay? And we will be integrating theta from 0 to 2 pi, okay? Now, what we're going to do is take this circle in the equatorial plane and rotate it pi radians, right? So it's like it's a little flap or something in a valve, right? And say if this big circle is a pipe or a valve, right now it's edge on, right, that equatorial circle, so the pipe is open. We're going to rotate it so it's closed, and then rotate it again until it's open in the other direction. So we're going to be rotating it pi degrees, right? and that will cover the entire volume of the sphere. So that means we're going to integrate over this little differential distance here, and that is r d phi, right? R d phi. So that's another factor of r and a d phi, and we're going to be integrating from 0 to pi, right? Okay, so let's start collecting terms. So, for example, let's start by moving this r up front here. So we will have, and let's go ahead and just write out the first integral, right? So we will have r squared, right? Because we're going to bring this one out front first, out front as well. So we'll have r squared dr, right? In our first, that's our first little integral, right? And so that is going to come out to be, let's see, 1/3 r, capital R cubed. Okay? Now let's take a look at our second integral, which we're going to do over d theta, right? So now we have this 1/3 r cubed out front, and now let's move out to the second integral here. And so that's 2 pi, 0 to 2 pi, and all we have is a d theta in here, which we're lucky. That's the only thing that depends on theta. So this is going to equal 1/3 r cubed times 2 pi, right, or 2/3 pi r cubed. Okay, now let's go ahead, and this is a constant with respect to our third integral over phi. So let's go ahead and do that integral out over here. So we're going to be 0 to pi, right? And out front we have 2/3 pi r cubed, okay? And inside this integral we have sine phi d phi. Okay, so this sine phi d phi, that is going to equal minus cosine of phi, right? Evaluated from pi to 0, right? So negative cosine of pi, well, cosine of pi is -1, so negative of that is just 1. And then we subtract cosine of, we subtract the negative cosine of 0. So let's go ahead and we're just adding then the cosine of 0, which is 1. So this equals 2, right? This whole integral equals 2. So we have 4/3 pi r cubed, right? Which is the correct, sorry, not area, volume, the correct volume of a sphere. Okay, so thanks for watching, and as always, don't forget to click to subscribe so you don't miss out on upcoming videos.